Hello all, welcome to the course Theory of Computation. In this video session, I will get you through the Chomsky hierarchy. Yeah, Chomsky has defined the hierarchy and he has classified the grammars in 4 different categories. Before getting into detail about the Chomsky hierarchy, let us discuss about what a grammar is because based on how a grammar production the Chomsky has defined the 4 different hierarchies. So a grammar has 4 tuples. We call them as V, T, P, and S. V standing for variables or non-terminals, and they are usually represented as uppercase alphabets A, B, or X, Y, yes, and so on. And terminals, they are usually represented by lowercase alphabets or some special symbols can also be used. So A, B, C, D, 0, 1, star, um, ampersand, and so on. So all these can be said as terminals, and these terminals cannot be derived any further. And productions or rules, this the format by which how a grammar should be. So which means I can have using this terminals and non-terminals, I can frame the productions like can have A derives AB, or I can write it as ABA derives BA, and so on. So I will have an LHS. The production should be of the form, and LHS left hand side should be present, a right hand side should be present, and for the derivation I use the symbol and arrow mark. So this is how the production of a grammar should be, and the starting symbol. So in a grammar there will be number of productions, and to derive a particular string, which is the starting point, is given by this start symbol. It is represented using yes. So let us get into detail about the different categories or different hierarchy involved in this Chomsky hierarchy. So this is the hierarchy defined. So he has defined as type 0, type 1, type 2, and type 3. So this represents the class of languages that are accepted by the different machines. So each type of grammar has its own corresponding machine that will accept such grammars. And this is defined by Noam Chomsky in the year 1956. So type 0 grammar, it is called as the unrestricted grammar, and there is no rule on how the production of that particular grammar has to be. So this language that represents this type 0 is called as Turing recognizable language, and the machine that accepts this type of language is called as the Turing machine. Type 1 grammar, it is called as context sensitive grammar, and the corresponding language it generates is called as context sensitive language, and the automata that accepts the type 1 grammar is called as linear bounded automata. And type 2 grammar, it is called as context free grammar, and the language it generates is called as context free language, and the automata that accepts this type of grammar is called as pushdown automata. And finally, type 3 grammar, it is called as a regular grammar, and the language it generates is called as regular language, and the automata which accepts this type of grammar is called as a finite automata. So type 0 covers all the other 3 types of grammar. Similarly, type 1 covers all the other type 2 and type 3 grammars, and type 2 grammar covers type 3 grammar as well. So let us now look into detail about the format in which each type of grammar will be. Type 0 grammars, this include all the formal grammars. The production of this type of grammar should be of the form alpha determines beta. Alpha belongs to any combination of both alpha and beta. They belong to the combinations of non-terminals and terminals. There is no restriction on the left-hand side and the right-hand side of the productions. Hence, these grammars are also called as unrestricted grammars. And the machine that accepts this type of grammar is called as a Turing machine. The language is also called as recursively enumerable language or Turing recognizable language. And we will be dealing about a special language called as recursive language. These are the languages which are accepted by a Turing machine, which will either accept the input and stop or reject the input and stop. But whereas in a Turing recognizable language or a recursively enumerable language, if the input is accepted, the machine will halt. If the input is not accepted, it may keep on trying again and again, thereby entering a loop. And the second category of grammars is type 1 grammars, and they generate the context sensitive languages. The grammar production is of the form alpha A beta derives alpha gamma beta. So you can see A here is a single non-terminal, whereas alpha and beta can be any combination of terminals and non-terminals. This A has been derived to this gamma part, but the context alpha and beta remains the same in both the left hand and right hand side. And the length of the LHS must be less than or equal to that of the RHS. So we should not have a production of the form alpha A beta derives alpha. Okay, which means the length of the LHS here is greater, which is not a valid type 1 grammar. And then it is context sensitive, which means with respect to alpha and beta, A has been derived to gamma. Yes, so if I have production CAT derives COT, then if I suppose use somewhere XACAT, in the next step, I can rename or derive it as XACOT. But when I get a different combination, like in suppose when I derive XACAB, I cannot change A to O now because C and T has not arrived here on either side. So with respect to this context, if A arrives, then it is possible to derive a O with respect to the context. Okay, so therefore this is one restriction which is imposed on type 0 grammar. If this restriction is there, then it is called as a type 1 grammar. So type 0 had no restrictions at all, and hence it is called as an unrestricted grammar. And here there is some restrictions that the left hand side should contain at least one non-terminal, and it should be with respect to the context, and the length of the LHS must be less than or equal to that of the RHS. Yeah. So the rule S derives epsilon is allowed if S does not appear on the right hand side of any rule. So we should not have something like A derives S. If we have a production like A derives S, then S derives alpha is, epsilon is not possible in a context sensitive grammar. The next type of grammar is type 2 grammar, and they generate the context free languages, and the rules is of the form the right hand side should be a single non-terminal, and the left hand side should be a single non-terminal which derives the right hand side, which is alpha. Alpha can be collection of terminals and non-terminals, and the production examples could be A derives a single A, small a, and A derives combination of terminals and non-terminals like this, and A can also derive epsilon. So this the automata that accepts this type of language is called as a push-down automata. In specific, it is non-deterministic, so we call them as a non-deterministic push-down automata. And a subset of this can be called as a deterministic context-free language, and which we call correspondingly the automata as the deterministic push-down automata. And about that we will discuss when we get into the topic push-down automata. Type 3 grammars, the last type of grammars, these generate the regular languages, and the grammar productions are of the form a non-terminal derives a single terminal, or a non-terminal can derive a single terminal followed by a non-terminal. So if this is the case, then it is called as a right regular. And if it is a case like A derives B A, then it is called a left regular. So these generate the same languages, which means those which is called as right regular and left regular, they generate the same class of regular languages. And the automata which this accepts this type of grammar are called as finite automata. So this is a comparison of all the different types of grammars and the machine that accepts it, automaton that accepts it, the language which is being defined by the given grammar, and the sample production rules, how it has to be for each type of grammars, and finally an example for each type of the grammars. In the next session, we will discuss about the central concepts of automata theory. Thank you.